Edexcel Core Pure, Calculus 4, Integration using partial fractions. Partial fractions recap. You may have already studied partial fractions, and we're going to revisit some of the ideas behind partial fractions before introducing the integration techniques. The idea is that an algebraic fraction that has multiple factors in the denominator can be split into the sum of individual fractions, depending on the nature of the denominator. So for example, x minus 9 divided by x plus 1, x minus 4 can be split back into fractions with denominators x plus 1 and x minus 4. And the fractions we would set up would be a over x plus 1 plus b over x minus 4. So this is expressing the problem as the sum of two fractions where the denominator is x plus 1 and the other denominator is x minus 4. So in this example, I am going to write this as the fractions a over x plus 1 plus b over x minus 4. And it's worth noting that these two algebraic expressions are identical to each other. So we're not solving this equation for x. They are identical equations, and we're trying to find the value of a and the value of b. So if I multiply through by x plus 1, x minus 4 on both sides, we get x minus 9 is identical to a x minus 4 plus b x plus 1. So notice when we multiply this term by x plus 1 x minus 4, the x plus 1 cancels out and we're left with x minus 4. And when we multiply this term by x plus 1 x minus 4, the x minus 4 would cancel out and we're left with just the x plus 1. Because this identity has to be exactly true for all x, we can now choose values of x. And by looking at this first bracket, x minus 4, a good choice of x would be let x equal 4. 4 take away 9 is minus 5. And why did we choose 4? 4 take away 4 is nothing, so the a term has disappeared. 4 add 1 is 5, so that's 5b, and therefore b must equal minus 1. Another nice value of x to choose is x equals minus 1. So minus 1 take away 9 is minus 10. Minus 1 take away 4 is minus 5a. And minus 1 add 1 at the end would give me 0. So a must be 2. So this algebraic fraction, x minus 9 over x plus 1 x minus 4, is identical to a over x plus 1, so that's 2 over x plus 1. And rather than putting plus minus 1, we can just put minus 1 over x take away 4. So try and avoid putting things like plus minus 1. That's a neater way of writing it at that point. And this is now ready for integration techniques to be applied. So the things to look out for each linear factor here, we have set up a partial fraction for each one. Then you multiply all the way through by x plus 1 x minus 4 to get this identity in x. And then I've chosen x equals 4 for my first value of x, which will make the a term disappear. And then we chose x equals minus 1 as our second method to make the b term disappear. And then we have separate fractions ready to be integrated. So in this example, notice we have a linear x minus 1, but we have a repeated x plus 3, so it's x plus 3 squared. So the partial fractions we would set up here would be a over the linear x minus 1, b over the linear x plus 3, but we'd also need a c over x plus 3 squared. So here we need two partial fractions, one for each of the powers involved on the x plus 3. So we've got an x plus 3 and an x plus 3 squared. We need both factors to be represented. Now when I times through by x minus 1 x plus 3 squared, the left hand side becomes x plus 15. When I multiply a over x minus 1 by x minus 1 x plus 3 all squared, the x minus 1 would cancel out and we'd be left with x plus 3 squared. And then moving on to the next one, when I multiply b over x plus 3 by x minus 1 x plus 3 squared, one of the x plus 3 factors will cancel out and we're left with x minus 1 x plus 3. And then when I multiply c over x plus 3 squared by x minus 1 x plus 3 squared, x plus 3 squared will cancel out and you're left with c lots of x minus 1. Again, this identity needs to be true for all values of x, so I'm going to start off with looking at these two brackets with x minus 1 in. I'm going to let x equal 1 as my starting method. 1 add 15 is 16. 1 add 3 and then squared is 16a, and then we've got 1 take away 1 in that bracket and 1 take away 1 in the last one, so they will give me zeros, therefore a must be 1. Looking at other values of x, if I look at this first bracket and this bracket, it would be very sensible to let x equal minus 3. So minus 3 add 15 is 12. Minus 3 add 3 is going to give me 0. Minus 3 add 3 is going to give me another 0. Minus 3 take away 1 is minus 4c. And once you've got the hang of this technique, you don't have to put the zeros in. I'm only putting those zeros in so you can see the thought process. So we found A and we found C. There are a couple of ways of finding the third constant, which is B. We could, for example, let x equal 0 is a perfectly good method. Just let x equal the value 0. But the method I'm going to show is a little bit different. I'm going to look at coefficients of x squared. Because this is an identity, an algebraic identity, the coefficients of x squared have got to match. So the coefficient of x squared on the left is 0. There aren't any x squareds. If I expanded this bracket here, I would have a lots of x squared. And if I expanded this bracket here, I would have b lots of x squared. So the a plus b x squareds on the right have got to be the same as the 0 x squareds on the left. So that's called comparing coefficients of x squared. And therefore, b must be the negative of a minus 1. So x plus 15 over x minus 1 x plus 3 squared, which is a pretty complex fraction, certainly something we wouldn't want to try and integrate, can more easily be written as a over x minus 1, so that's 1 over x minus 1, and then we've got b over x plus 3, and again try and avoid writing plus minus 1. I'm just going to write minus 1 over x plus 3, and again c over x plus 3 squared is just minus 3 over x plus 3 squared. Again, this is ready to be integrated if necessary and would be easier to integrate. So the key message from here is that this linear factor just has a linear partial fraction, but this repeated factor needs both the linear and the repeated case as separate fractions in the partial fractions. Once you've multiplied through by this denominator, x minus 1, x plus 3 squared, look for sensible methods. So looking at these brackets suggests x equals 1 would be a good method. Looking at these two brackets suggests x equals minus 3 would be a good method. X equals 0 would also be a good method, but just to show you that there is an alternative method, I've picked out the coefficients of x squared. There are no x squareds on the left hand side. There are a x squareds there, and a was 1, and there was bx squared there, so that gives us b. So a quick summary there. If there's a linear factor in the denominator, that can go with just a constant in the numerator. But if there's a repeated factor like this one, you need a factor, a separate factor for each of the two possible powers. So we've got x plus 5 to the 1 and x plus 5 squared, as separate partial fractions. So if we were dealing with linear factors in the problem, we would just have separate fractions, one for each factor in the original. However, if there's a repeated factor in the problem, then you need one partial fraction each for the possible powers that have been repeated. So for example, if the denominator had a factor that was cubed, you'd need a over the linear, b over the squared, and c over the cubed brackets. Then you multiply all the way through by the denominator, that's the left hand side and the right hand side, and then you select values of x which create helpful zeros on the right hand side. So you look for helpful values of x to make the working as easy as possible. If necessary, you could let x equal 0 as a third method, but quite nice is to look at the coefficients of powers of x, particularly the x squared coefficients is often the easiest one to find. In the next session, we're going to be looking at partial fractions where the denominator is in the form ax plus b times cx squared plus d.